Good morning, students. Today we're going to take a look at lesson 4 of the space unit. Should be a relatively easy lesson. Going to be a little tiny bit of math involved, but it should be relatively simple math. Okay, so we're going to take a look at meeting our solar system. Okay, which is kind of the neighborhood that we live in, and of course, as per usual, there are questions for you to complete for homework. The answers will be posted in the LMS, but of course try them on your own before checking the answers. Okay, so the planets. The ancient Greeks were the first to notice that there were 5 objects that appeared to wander through the constellations. So the constellations, those patterns in the sky, the patterns of stars that we notice that kind of orient ourselves, we noticed there were these 5 objects, 5 little pinpricks of light that seem to move through those constellations. And you can see them without binoculars or a telescope. Okay, and those 5 planets, those 5 objects we now know as planets, happen to be Mercury, Venus, Mars, Jupiter, and Saturn. Okay, 5 of the planets. Now, these objects were not fixed around the background. The stars are. The stars not really fixed, but because the distances are so great, it appears as though the stars are fixed where they are. They don't move. Okay. Now, for that reason, we called them planets, because planet is derived from the Greek word for wanderer. Okay, so a planet is an object that orbits a star. Actually, it can orbit one or more stars. Okay, and cannot be a star itself. It's usually spherical. Okay, it does not share an orbit with another object, which is important. Okay, the not sharing an orbit with another object is important. Okay. There's one thing in here that's a little tricky. It says an object that orbits one or more stars. So the planets in our solar system orbit one star. But in a lot of solar systems out there in the universe, in different galaxies far, far away from us, many solar systems are actually a system of 2 stars. And those 2 stars orbit around each other. And then the planets in the solar system orbit around those 2 stars. Okay, so we call those binary stars, in which they orbit around each other, and then planets then orbit around those 2 stars. And that's actually fairly common in our universe. I think it's a little less common to actually have only 1 star. Okay, so but bear that in mind. If it's spherical, it doesn't share its orbit, and it orbits around a star, then that's really the general sense of it's a planet. Okay, so we consider the planets, the sun, and other small objects, that's our solar system. Okay, so our solar system, there's the definition, a group of planets that circle 1 or more stars. Okay, so there are 2 models of our solar system that we've had in our history. The first one is the geocentric model. Geo means Earth, centric means at the center. Okay, so this model was the first model that we developed. And basically, the general thought was Earth was the center of the motion. So all those planets were orbiting around us, the Earth, including the sun. The sun was another body that, according to this model, orbited around us, the Earth. Now, is that accurate? No. Okay. This was based on the work of a Greek astronomer named Ptolemy, and it actually remained in place for about 1,500 years. But it's wrong, okay? And we had a real hard time convincing the powers that be that this model was wrong, but it is. And we know it is. We know Earth is not the center of the galaxy. We know it's not the center of the solar system. We know it's not the center of the universe, despite what we may think, okay? But the fact that we exist does not make our planet the physical center of the solar system, okay? But that's what we wanted to believe for many, many, many years, okay? But then came around a guy named Nicholas Copernicus, and he developed the heliocentric model, and it's such named because helio means sun, okay? And this model states that the sun is actually at the center of the solar system, and the planets, including Earth, orbit around the sun. Okay. Now, he thought they were perfect circles. Okay, which I mean, logically, I guess kind of makes sense. If you're going to make an assumption, I would too. I would have assumed, oh, it must be in a circle. Okay, and it wasn't until a guy named Johannes Kepler, he came around, and he's the guy who actually timed out, okay, he was timing out the orbits based on all these celestial bodies and comparing that with gravity. And there are mathematical formulas for gravity that you'll learn in grade 11 and 12 physics to kind of mathematically model gravity. I was comparing that with the timing and basically saying, well, hold on a minute. The timing doesn't make sense with what we think the mass of these planets might be, and so circles doesn't really work. He was the guy who said, you know what, mathematically, the orbits would make more sense if they were ellipses, which is obviously what we see now, and we can directly observe that because we've got satellites and we've been to space now. Okay, so now these guys, Copernicus, Kepler, another guy was Galileo, who was an Italian scientist during the Renaissance. These are guys that said, okay, Earth's not the center, the sun is the center. And it took a long time for them to convince the powers that be. And many of them were condemned, actually, for saying, no, the sun is the center of our solar system, not the Earth. They were condemned for saying that, but it was the truth. Okay, so just a side story about kind of the adversity that some of these scientists, some of these early astronomers faced in defining the model of our solar system, one that we actually know to be true today. Okay. Now, classification of the planets. In this picture, you will see 8 planets: Mercury, Venus, Earth, Mars, and then in between them, follow my cursor here, there's an asteroid belt. And then we have the last 4 planets: Jupiter, Saturn, Uranus, and Neptune. Okay. Now this diagram shows the planet size to scale. So in other words, Jupiter is that much bigger than Earth. It is to scale. And then there's the sun, and so you can sort of compare how much bigger, the sun is than each of these planets and how much bigger the planets are than each other. What's not to scale here is the distance. Okay, they've crammed all these planets together just to get them in one animation, one little picture. But in fact, the actual distances between these planets is pretty big. Okay, and you wouldn't be able to fit them on a scale diagram here. And so they've kind of scrunched them all together. So what's accurate is the size comparison. What is not accurate is the distance between them. Okay. Here's how we classify the planets. Those inner planets, okay, Mercury, Venus, Earth, and Mars, they're closest to the sun. They're small, okay. They have solid cores and they've got rocky crusts, okay. So we call them terrestrial planets. Terrestrial meaning Earth-like, okay. After we get through those first 4 planets, we hit the asteroid belt, which is literally a ring of asteroids that's orbiting our sun. And on the other side of that asteroid belt, there are the outer planets: Jupiter, Saturn, Uranus, and Neptune. And they're further from the sun, okay? And they're formed by large clumps of gas, ice, and dust. And for that reason, we call them the gas giants, okay? And they're really well known for, number one, being quite cold, because they're farther away from the sun, and also for the gaseous bands. So again, if we look at Saturn and Uranus, they have the rings around them, okay? And that's sort of a defining characteristic. Neptune has rings. They're very, very faint as well, okay? And that's sort of a well-known characteristic. But they're made of gas, and they're very, very large, okay? So we call them gas giants. Not creative names, fairly obvious names, okay? Now, planetary motion. We know that the planets are all orbiting the sun. We know that, okay? But they're orbiting the sun at different rates, okay? So one of the things we notice is that when Earth is usually on an inside track, because Earth is one of the closest planets to the sun, it's the 3rd rock from the sun, okay? When it catches up to an outer planet and moves between the outer planet and the sun, the planet, so the other planet, not Earth, the other planet, appears to make a looping motion, okay? Which is shown for Mars below. So that's like saying this is Earth, okay? And this is Mars. So they're orbiting. Earth catches up to Mars and passes Mars, okay? So now it's in between the outer planet and the sun. So I'm going to do this again. Earth, Mars, in between, right in between the outer planet and the sun, okay? When we look at it from planet Earth, it looks like that outer planet is making a looping motion. And so that's what we see here in Mars, is these are days, by the way, or different points, okay? 1, 2, 3, 4, 5, and it looks like it makes a big loop here. It's not making a loop. It's only because Earth is passing it that observing it night after night makes it seem like there was a loop, okay? And we call that retrograde motion. And it looks like it's east to west rather than the normal west to east motion, okay? But it's really not. It's just the way we perceive it because one planet is passing another planet, okay? It's just the way we perceive it night after night, okay? So I'll probably post, hopefully I can find a good YouTube video to post for that so you guys can actually see that in motion, demonstrating that retrograde motion, okay? Now, the distances between planets. Planets lie so far apart from each other that kilometers are not a meaningful way to measure the distance between them. Okay, so we have a special unit, we call it the astronomical unit, AU, to help us grasp these units of measurement. Now, here's where it comes from. The average distance, and we know that distance changes, but the average distance between Earth and the sun, okay, is 150 times 10 to the 6 kilometers, or 150 million kilometers, okay? 150 million kilometers. So that's the average distance between Earth and the sun is 150 million kilometers. And we say that's one astronomical unit, okay? 150 million kilometers, okay? So the average distance between the sun and any object that's orbiting the sun is called its orbital radius, okay? And it's typically expressed in astronomical units. So there's a little bit of a calculation, and it's basically just a quick division. All right, so here's your example, and I put the solution on the next slide. I didn't do it in motion, I just wrote it out so you can see it because it's really just one step. If the distance between the sun and Jupiter is 778,300,000 kilometers, what is the orbital radius of the planet? That's the question that we have to answer, okay? So you can try it. Maybe you can try it and you can kind of figure it out, but I'm going to put the solution on the next page and show you. So if you want to pause the video, go ahead and pause it, but I'm going to move on right now. Okay, here's our solution. Here's what I did. I did a unit analysis. So I know my final unit has to be in astronomical units. I know that. So I take my 778,300,000 kilometers and I write it down and I multiply it by a fraction or a ratio. Okay, and the ratio that I multiply it by is one astronomical unit over top of 150 million kilometers, because I know that that's the ratio between those two units. One AU is 150 million kilometers, and I know that I need AU to be my final unit, so I have to put astronomical units on top, okay? And so what happens is I end up canceling out the kilometers, so the only unit I'm left with is AU, astronomical units, and then I just do my division. So I do 778,300,000 divided by 150 million, okay? Because it's 1 over that value, okay? So really, I mean, that's just, if I remember my rules as far as multiplying fractions are concerned, that's how I end up with this stage, this step right here, okay? And when I do that division, I end up with 5.1866666 AU. I round that to 5.19 AU, 2 decimal places. Why 2 decimal places? Well, I just decided it was 2 decimal places. Maybe you'll learn how to properly round in the summer AP science class, which I'll be teaching online. So you will learn how to round properly, but for now I just arbitrarily decided 2 decimal places. And then I conclude by saying the orbital radius of Jupiter is about 5.19 AU. Okay, so now I made this more complicated than I had to because I wanted to show you the unit analysis. But anytime you want to take something that's in kilometers and turn it into astronomical units, you just divide by 150 million. That's it. Okay, that's the only thing you have to do. Okay, so that's actually the end of the lesson. It was a little bit of a shorter lesson, and hopefully I'm going to try to keep the space lessons on the shorter side rather than the longer side as far as these videos are concerned. But that's it. Make sure you take care of the homework that I've assigned there at the beginning of the PowerPoint presentation, and that you take care of yourselves and take care of the people that you care about. Stay healthy, stay safe, keep studying, and bye-bye.